So here's an example of what differential calculus is all about. We've got Betty. She's biking down the road, and she's kind of a math person, so she does this funky formula right here about the number of feet she travels in t seconds. So she's also got a little bit of a strange friend. The strange friend pops out and takes her picture exactly 10 seconds after she started. And the question is, how fast was she going right at that time? So we went ahead and graphed this. The graph of the distance as a function of times looks like this. Realize this is seconds. And if we look at the average rate of change between the 0 second and the 10 second, we'll actually get the slope of what we call the secant line between 0 and 10 seconds. And finding that slope, we actually get 4.5 feet per second. The key thing is realizing that's not how fast she was going at 10 seconds. That's the average speed in the first 10 seconds. So on average, she was going 4.5 feet per second those first 10 seconds. But if you think about it, it looks like she's going to be going faster than that at 10 seconds. She should be going faster than 4.5 feet per second. A better estimation would be if we could make the time shorter. So let's look at what happens if we go from 9 to 10 seconds. I've gone ahead and put the points in there. So the slope we get there of that secant line is 8.1 feet per second. Notice it is indeed faster than 4.5. And at the same time, it looks like the curve itself. So let's zoom in. It's not actually quite the same. Zooming in, that blue line, see it's on top of the red. The blue line is the secant line. The red line is the graph itself. You can see that it is different. And Betty is still speeding up as she's continuing past 10 seconds. So 8.1 feet per second is closer, but she's still going faster than that at 10 seconds. So let's actually get closer. Let's do a smaller time period. How about 9.9 seconds to 10 seconds? So if we go ahead and find that slope, it's 8.46 feet per second. Again, faster than the 8.1 feet per second. And let's go ahead and zoom in again and see what we got. I'm going to look at this part of the graph right there. And the difference between the secant line and the graph itself in that window is so insignificant that they look like the exact same thing. So let's zoom in a little bit more. I just want to show you that it is indeed different. And if you zoom in quite a bit, you can see that the blue line is still above the red line. It's not quite the same. And that's because the red line is curved, and of course the blue line is, well, a line. It's straight. So we still have a good approximation. It's pretty good at that point, but we can always get closer and closer and see better and better. So probably the next thing we want to do is go from 9.99 seconds to 10 seconds. And at this point, it's getting so small, the time period is, that it's hard to even see it on the graph, even if we zoom in. So let's go straight to the table. So what we've done so far in terms of calculating the average speeds, there's our 4.5 to start. And then the 8.1 and the 8.46. The thing we talked about next was 9.99. If we start there to go to 10, you can see we're getting a little bit bigger than 8.46. We can even get closer. 9.999, 8.4996. You can see the average speed is there. And we can even start getting ridiculous. We're talking about 9.9999 seconds to 10 seconds. And there's our average speed in that time period. And let's do one more time just to be kind of silly. It's kind of silly because already you can see that it's heading towards 8.5. So it sure looks like the average speed is 8.5 feet per second. And that's going to be our guess for the exact speed when her friend took her picture at 10 seconds. 8.5 feet per second. We'll figure out how to do this explicitly and algebraically with mathematics also, but we just wanted to get the idea of what we're going to be doing in calculus.